The second application of the Gauss law is to find the electric field due to a uniformly charged spherical shell. Okay, uniformly charged spherical shell. So first of all, what is a shell? Do you know what is a shell? A shell is nothing but any object that has a cover and inside it is hollow. Okay, it's hollow inside. There's nothing inside. It has only the cover. All right. The best example is a ball, like a football or a basketball. Okay, there's nothing inside. There's just air inside. Got it? So here also we have a spherical shell. Okay, a spherical shell. Eggshell is what? Eggshell is not spherical, right? Somewhat oval, right? So, but here we will take a spherical shell. Okay, so let's say, let me clear off this part. I don't need this part. All right. So first of all, we will find the electric field outside of the shell. Okay, let me draw the diagram. So let's say you have let's do number one first. A. First of all, we'll find the electric field outside the shell. Okay, so imagine this to be the spherical shell. Okay, and since this shell is uniformly charged, so what will happen? It will have positive charges equidistant. Okay, uniformly charged. So let's say the total charge present in the shell is Q. Okay, Q is a total charge. All right, so these positive charges are spreading out on the surface of the shell uniformly. Okay, now we want to find the electric field outside of the shell. Let's say at a point P. At a point P. Okay, this point P is outside of the shell, right? So from the center of the shell, what is the distance of this point P? From here till here, the distance is small r. Okay, and let us take the radius of the shell to be capital R. O is the center of the shell. All right. Okay, now what do we do? Let me shorten this because it will be a little bit, it's too long. Okay, let's say this point is point P. Okay, what do we do? So just like before, just like in the first application, we have to draw the Gaussian surface. Can you guess what would be the shape of the Gaussian surface? I told you the idea. Look at the geometry of the problem, geometry of the body. This is a spherical body. So what type of Gaussian surface? A spherical Gaussian surface. Okay. So let the Gaussian surface be spherical. So we have to draw the Gaussian surface passing through point P. Okay, spherical in this shape. Please draw this nicely. The surface that I'm drawing is not very good, so I cannot draw a better diagram than this. Please draw this nicely. It should be a sphere. Please use your compass while drawing this diagram. Got it. So what is this dotted surface here? This is the spherical Gaussian surface. Okay, then what do? We have to select a small area on the Gaussian surface. Remember, the area must always be where on the Gaussian surface, not on the shell, on the Gaussian surface. The area vector, this area is facing upward, it is facing in this direction. So the area vector ds will be in that direction. Got it? Now what will be the electric field passing through this area? What will be the electric field? I told you the electric field is always emerging perpendicularly from the surface. So this line is also perpendicular from the surface. So therefore the electric field will come out in the same direction. It will be going in this direction, same direction, E bar. Understand what is E bar here? It is the electric field that passes only through this small area ds. Is it clear? Okay. Now by Gauss law, we have integration E dot ds q by epsilon naught, right? So here again you will have to apply the dot product. A dot b is equal to ab cos theta, right? So this will be E ds cos of the angle between E and ds. Look at the diagram, E and ds pointing in the same direction. So what will be the angle between them? That would be 0 degree, q by epsilon naught. Okay, cos of 0 degree you know very well. This part will be equal to 1. So you have just E ds is equal to q by epsilon naught. I can take E outside because E depends on the distance. See, everywhere the distance is r same, no? Constant. So therefore since E is constant, I can take it outside. I am integrating only ds, q by epsilon naught. Can anyone tell me the value of this integration? What is the value of this integration out here? This one, you are integrating ds. What is ds? ds is this small surface. You're taking a tiny surface on the, imagine a ball, okay? And you're drawing a small surface on the ball. When you integrate that surface, what will you get? You will get the entire surface, no? Entire surface of the sphere. And that surface of the sphere from your mensuration is 4 pi. Radius of the sphere is small r square. So this will be E into E into 4 pi r square q by epsilon naught. So therefore E is equal to q by 4 pi epsilon naught r square. Let's call this equation 1. Yeah, I want to put this inside of a cloud. This is an important equation. All right. Okay, now let me write here. Okay, right. But what is Q? What is Q? What is Q? Okay, what is sigma? What is sigma? Sigma here is 1. Do you remember the name of sigma? Sigma here is surface charge density. Surface charge density means what? Means charge divided by the surface area. Surface area, okay. Now surface area of 1. Of that surface containing the charge. So which surface contains the charge? It is this, not the Gaussian surface. Gaussian surface is just an imaginary surface which does not contain the charge. This one contains the charge. So sigma here will be charge is Q. And what is the surface area of this? Again, this is a sphere. So it will be 4 pi capital R or small r, radius of the sphere, r square. So therefore Q will be 4 pi r square into sigma. Call this equation 2. Let's substitute Q here. So therefore you have E is equal to 4 pi r square sigma by 4 pi epsilon naught r square. You can cancel 4 pi and 4 pi. Yeah, so you get E is equal to sigma capital R square by epsilon naught small r square, and this is outside, so let us write E out. E out. Okay, so this is the required expression. Call this equation 3. That is E out. This is how does it vary with small r? Inversely proportional to r square, right? Because sigma is constant, capital R is constant, epsilon naught is constant, only small r you can take any value of small r. So E out is inversely proportional to 1 by r square. Okay, so that is the first part 1, that is outside. Okay, part 2, did we take part A, part B? Okay, let me take this also as part B. Part B, on the surface. On the surface. Oh, alright, so let's say if I take this point P and I put point P here. If P is out here on the surface, then what is the distance of P to O? That means what is the value of capital R? Capital R here is 1. What does capital R denote? It denotes the distance from P to the center. No. Now I push this P down here. What will be now the new distance from P to the center? Is it not equal to the radius? Yes. So you write like this. You say on the surface. On the surface, the value of R is equal to capital R. So therefore, what will equation 3 look like? E will be sigma by epsilon naught. Okay, sigma by epsilon naught. Why? Because this capital R and the small r will cancel out. All right. And if you compare equation 3 and equation 4, let's look. Equation 3 is like this, and it is divided by something out here, no, by r, right? It is divided by r, but here it is not divided by r, which means now it means that if r increases, E naught will decrease. In other words, if r decrease, then E naught will increase. Okay, so if you look here, it is divided by r, here it is not divided by r, so that means that this part here is actually the maximum value. Why? Because it's not divided by anything out here, by an extra term out there, no? If you compare, it's not divided, right? So if you look here, this E out, let me work out this one for your understanding. E out is, if I divide E out by this part, okay, let's take E dash, okay, what will I get? E out by E dash, this will give me sigma r square by epsilon naught r square into epsilon naught by sigma. The sigma will go, epsilon naught will go, so again r square by small r square, isn't it? So from here it is very clear that this ratio is less than 1, no? It's less than 1, right? Why? Because this small r is larger than capital R. It's very clear from the diagram, isn't it? Here. So this means that E out is less than E dash, or you have E dash is greater than E out. Okay, so what does this mean? It means that E dash is larger. It is in fact maximum. Okay, let me clear off this spot. Okay, so that's on the surface. What about inside now? Let's see, inside the shell. Inside the shell. Okay, we draw the diagram once again. So we have the shell like this. Okay. Okay, where the charges? The charges are outside. Remember this, okay? Remember, for a conductor, the charges are always outside of conductor, on the outside, the outer surface of the conductor. There is no charge inside of conductor. Okay, please remember that point. All right, now let's say point P is somewhere here. Point P is there. This is the center. So this radius is capital R. This distance of P is small r, and that is all. So what do we do here? Again, here also we have to draw the Gaussian surface, but then the Gaussian surface will be passing from P. So the Gaussian surface will be inside, like this. All right, inside. So therefore, what is the let's apply Gauss law. By Gauss law, you have integration E dot ds is equal to q by epsilon naught. All right. So let's imagine we don't know the electric field. Let's imagine that let us take the surface out here, and the surface is pointing in that direction, ds. Let's imagine that the electric field is also pointing in that direction. Okay, so that is E bar, right? So again, we work out the same maths out here. We will get E ds cos 0 degree q by epsilon naught. Right, and then we know that this part is 1. Then E we can take it out. ds is equal to q by epsilon naught. Okay, then again here the value of ds will be 4 pi capital R square is equal to q by epsilon naught. But then, okay, or we can write E is equal to q by epsilon naught 4 pi R square. But then what did I tell you? Inside, is there any charge present inside here? There's no charge present inside. You can see that the charges are residing only on the outer surface. So this will give you 0. Why? Since Q is equal to 0 inside the shell, because the shell here is a conductor. Alright, so E in here is 0. Do you see here? So we understand that inside of the shell there is no field. Field is maximum on the surface, and then as you go away, how does the field vary? It varies like this. So if you are asked to draw the graph, so this graph, electric field with distance. So this distance is r. Okay, let's say this is the sphere. Okay, we don't need to draw the sphere, but let's just for our understanding. Okay, let's say that is a sphere. This is the center of the sphere. Now, at this point, the value of r is capital R, right? So inside the field is, let me use pick. So inside the field is 0, so it will come along this line. It will come along this line here. Okay, just on the surface the field is maximum, so that means the field will be from here. It will be maximum at this point. And then outside, as you go out, how does it vary? Inversely proportional to r square. So it'll vary like this. It'll go like this. Okay, here E in is 0. Let's call this E in. Then this is E on the surface. E on the surface. I should wait. Let me rub this off. It's maximum here. From here it goes like this. So on the surface the value of E is how much? E is equal to sigma by epsilon naught, and then outside, out inversely proportional to r square. So this is another important application of the Gauss law, and this graph is also important. It is usually asked in the exam. Okay, just a revision. what did we do? First of all, we consider we will find the electric field outside of the shell. So for that, what did we do? We take a point P outside, and then we draw a spherical Gaussian surface passing through P. By Gauss law, we have this. We apply E dot ds is equal to q by epsilon naught. And then you can clearly see we apply the A dot B formula here. You get E ds is equal to cos 0 degree. Why 0 degree? Because the angle between this and this theta here is 0 degree. Okay, cos 0 is 1, E is taken out, then integration of this is 4 pi r square, right? So you get this equation 1. Then you use this one, the definition of the surface charge density. You will get Q, substitute Q in equation 1. Finally, you'll get equation 3. So E out is inversely proportional to r square. On the surface, that means when you take this point P and put it here, the value of small r will be equal to capital R. Okay, if you don't understand that, you please go back to that point where I discussed to you this one. So if r is capital to small r, then this part and this part will cancel. You will get sigma by epsilon naught only. That is maximum. Inside of the shell, what did we do? Inside of the shell, we consider a point P. Now we consider it inside, right? And we draw the Gaussian surface inside of the shell. Again, we apply the Gauss law. So E dot ds. And what did we do? We take a small area out here. The direction is ds. And we assume that the electric field is also in that direction. We don't know. Okay, we just assume. So here, again the value of the angle theta is 0. So I'm getting 1 out there. So E I'm taking out. ds 4 pi r square. Oh, sorry, this is not capital R. This is small r. This is small r, but it doesn't matter. Control Z. This is small r. This part also will be small r. Okay, right. Why small r? Because this area integration is done where? On the Gaussian surface, is it not? And the radius of the Gaussian surface is somewhat small r. Okay, so therefore 4 pi small r square. So E is this much. But then what did I tell you? The charge inside is 0. So therefore En is 0. Then you draw this graph. Okay, practice this nicely. Thank you.